Okay, all right, let's begin. So we are here to learn about electrical and electronics. As I'm sure everyone is aware by now, CPE majors are required to take a sequence of 3 classes. They are known as electrical and electronics 1, 2, and 3. 115, 215, 315. So a little bit of background and history. EE students and CPE students, no matter where you are in the world, learn about circuit analysis and electronics. EE majors will learn about circuit analysis for one entire academic year. We'll learn about electronics and semiconductors for another entire academic year. So 3 quarters and then another 3 quarters. Up until a few years ago, CPE majors here at Cal Poly would take those first 3 circuit analysis classes and would take the first 2 of the 3 electronics classes. A few years ago, CPE department said that's too many. Let's modify the curriculum a little bit. And so they tasked the E department, and in consultation with both departments and faculty and curriculum committees and everything, they decided they would not compress, but they'll reconfigure the classes from 5 to only 3. So instead of spending 5 quarters taking those classes, CPE majors now spend 3 quarters. Okay. And so Dr. Prodanov, who is currently the chair of the EE department, he was the one who designed these courses. He put in a tremendous amount of work to get these done. Because it's, just to design one chapter of a class, it's a big deal. Just to design like an entire course is a huge deal. And then, I don't know, tremendous, more than huge, designing 3 lecture courses and 3 entire lab classes. So all 6 of them were designed. And obviously, this is not a unilateral decision. It's basically in consultation with the entire, with the EE departments as well as the CPE departments. But he's the one who came up with everything, like the slides, the material, the homework, exams, and everything. So that's the bit of history about, how and why CPE majors at Cal Poly are taking these classes. The second part of that is that no matter who teaches it, we are required to follow those rules. That's actually true for any instructor in any university. Once the department and the academics or the academic curriculum committee has designed a course, no matter who teaches that course has to stay within the structure and confines of that course. Okay, so at our level, at lower level, you might see Prodanov's name on some of the slides, and that's because he's the one who has designed these. And all of us who teach it, we have to follow those. The next quarter, I believe you'll be taking 215, being taught by a different instructor. But again, the same slides that are designed by Dr. Prodanov. Right. Okay, so let's go to our class notebook. Class notebook is one of the ways where you can access your slides. The slides page on Canvas is not yet up because I'm modifying some of the slides in some minor ways. So the 2 ways you can access the slides are from the front page and from the class notebook. The class notebook is, of course, available to everyone. You're automatically enrolled. Everyone was added on, and so it's already available at your end. Okay. All right. So first one, Intro to EE, Electrical Engineering, or Electrical and Electronics Engineering, EEE. No matter what scientific or engineering field we are working in, we always require math, right? So the first thing up there is there's some required math knowledge and some skills, right? This is especially true of mechanical engineering as well as electrical engineering, okay? So EE is concerned with dependencies. It's also concerned with a lot of functions. Now, dependencies, we have a system, electrical system, and we have if you break it down into 2 broad categories, any electrical system has a source or multiple sources, and it has some loads. Sources are the ones that supply energy. Loads are the ones that receive energy. Okay. In this energy transfer portion that takes place between the source and the load, everything follows the law of conservation of energy. Energy is neither created nor destroyed. It's only transferred from one one form to another. So in an electrical system, more often than not, we are transferring electrical energy into thermal energy, heat. Let's take the simple example of like a flashlight. Flashlight has what? It has a source, which are the batteries. There's the load, which is the light bulb. When you when you turn the switch on, you flick the switch on, light bulb turns on, battery is connected to the light bulb, electrons are flowing through the circuit, voltage is applied, current is flowing, light bulb starts glowing. Some portion of that energy or electrical energy is converted into light. Some portion is converted into heat. Old time filament light bulbs used to get hot. Anyone ever feel a filament light bulb? Right? It's hot. So it's dissipating light as well as heat. What is it doing? It is converting electrical energy into two different kinds. Okay. And so EE is concerned with dependencies. We are converting one physical quantity into another. And then because it's concerned with transferring or changing, mathematically, we describe it with a lot of functions. And those functions, the primary ones are summation, differentiation, integration. When we get to capacitors, inductors, we use differential equations, hence ODE, ordinary differential equations. And so these are the basic math skills that would be required. Okay. All right. So I spoke about circuit analysis classes and electronics classes. This is, of course, referred to as electrical and electronics. Now, typically, when we learn about circuit analysis, you only learn about three components. We learn about resistors, we learn about capacitors, and we learn about inductors. So capacitors, resistors, and inductors. And then we learn about semiconductor devices under the umbrella of electronics. So then we have diodes, we have transistors, BJTs, FETs. Those are things that you will encounter in 315. Okay. So typically EE majors do not learn about diodes or transistors in circuit analysis classes. In 115 though, we will use diodes for some portion. Okay. So if you have already picked up your lab kits, you will notice that I believe there are some diodes in your lab kits. I believe you performed some experiments with diodes. I'll have to take a look again if anything has changed. But as far as I remember, 145 does have some diode experiments. So we won't go in depth into the diodes. It's just a two terminal device. And so we'll just refer to it and talk about it a little bit. But you'll be learning the details in 315. Okay, so these systems are implementing complex functions. We have a system that comprises of source or multiple sources, multiple loads. That system could be small, that system could be large. When we used a graphical means to describe the system, we draw it out, whether it's by hand or whether it's on a computer, and we label that as a schematic. Okay, so a schematic that describes an electrical system is known as a circuit diagram, or just circuit for short. So we use schematics to graphically represent circuits and networks. We refer to it as a circuit diagram. Now, at a small scale, we just say this is an electric circuit. Again, source and a load, and perhaps a controlling mechanism like a flashlight, like a simple circuit diagram. So if I was to use that as an example, I would have a source And I'm going to draw a filament light bulb. This is a filament light bulb. And then as a means of controlling this, we have an electrical switch. No matter what kind of flashlight you pick up, that is essentially what is inside that circuit. So this diagram right here is a schematic that describes the electrical system of a flashlight. And this is known as a circuit diagram. Okay. So you take a small system, small electrical system, use graphical means to describe it. That schematic is labeled as a circuit diagram. Now, when circuits are small or simple like these ones, we simply refer to it as a circuit. But larger systems, sometimes they're often referred to as networks. And so we have the word networks. Lower level, smaller circuits, we call them circuits. Higher level, we call them networks. However, there is no in real life, I've seen that sometimes the lines between what is known as a circuit and what is known as a network sometimes could get blurred. So for instance, the circuit analysis classes here are referred to as circuits 1, circuits 2, 1, 2, and 3, right? Circuits. When I went to grad school in Louisville, the exact same class over there was known as network analysis. Instead of circuit analysis, it was labeled as network analysis. Studied the exact same topics, used the exact same books. Different name, but the exact same thing, right? Okay. All right. Then electrical and electronics. So typically electric circuit analysis refers to resistors, capacitors, inductors. Electronics typically refers to semiconductor devices labeled as, not labeled as, such as diodes, transistors, and FETs. That's the clear demarcation. But in modern times, electrical and electronic, there is no clear demarcation or delineation. Okay. As an example from a different country, I'm from India. I studied the exact same things that you are studying more than 35 years ago. But in India, I'm an electrical engineer here. In India, they would call me as an electronics engineer. They would not call me an electrical engineer. Electrical engineering in India and those parts of the world refer to, well, engineers like us who specialize in power systems, like the power transmission lines, transformers, power generation, power distribution. Those are the ones that are referred to as electrical engineers. But outside of those areas, North America and pretty much most parts of the Europe, electrical engineering is an umbrella term that encompasses everything underneath it. Electric circuits, as well as electronics, semiconductors, everything. All right, let's take a pause. Let me know if you have any questions so far. Any questions? All right. Okay. All right. So let's talk about a bit more about the functions, and then we'll look into the quantities. Okay. So the functions that we sometimes look at are mostly constant. Some of them are proportional, linear, and then some of them not a function. Constant refers to the fact that the value of that function is constant with this reference point. Okay. In electrical engineering, Oftentimes when we plot our signals, we're plotting them with respect to time. So time is on the x-axis, and then you have the value of that quantity on the y-axis. So if we take a simple battery, let's say, for instance, a typical battery, what is the voltage of a typical AA sized battery? Anyone know? It's printed on the side. That's a good guess. So the small coin cells, coin batteries, or look with the ones that look like a coin, those are 3 volts. There are some other ones that are also 3 volts. There are also some ones that are higher than 3 volts. But for the most part, a typical AA size battery, a AAA size battery, C cells, D cells, all of them are 1.5 volts. Okay, so it's 1.5 volts. Now, if you plot the value of that battery as a function of time, what is the value? What is the value of that battery at 8 o'clock in the morning? 1.5 volts. Now, about 8 o'clock at night? So 1.5 volts, theoretically speaking, right? So if you plot it, it'll look something like this. It's a constant value with respect to time. However, if you take your power outlets, the power outlets that are all around you in the classroom, they're on the lab benches, they're also above you. Those power outlet voltages, they change their value as a function of time. All right. Those are sinusoidal in nature. They go up, they go down, and it's known as a sine wave. And we'll talk more about that later. Don't need to get into it right now. But those are known as sinusoidal waveforms. Those functions are not constant. Sorry, not functions. The value of that quantity is not constant. It changes with respect to time. And the function, the name of that function is known as a sine wave function or a sinusoidal function. Okay. And so we'll learn a little bit more about that later. All right. How about linear? You know what this equation is, right? You've studied this in physics before. I'm assuming you have taken physics prereqs, right? This is Ohm's law. Ohm's law was named after, I believe, a British physicist. Unless I'm mistaken in his nationality. His name was George Ohm. Now, one thing you should remember is no matter what kind of scientific discovery or any kind of discovery on this planet we are talking about in this world, a lot of people made a lot of effort over a long period of time. But sometimes it so happens someone, well, due to one reason or another, one person takes the attribution. So if you do a lot of work and you make a big discovery, then no matter how many people came before you, that major discovery is tied to that person. Okay, so it's the case with this Ohm's law. George Ohm did conduct a lot of research into the properties of voltage and current as pertains to a resistor, and came up with this law where he said that the voltage is directly proportional to a current. So as pertains to a resistor, the voltage and current are directly proportional. Now, there are a lot of people who did a lot of research before him, and there are a lot of people who did the research after him. So he did not come up with this out of thin air. He based his work on other people. And so that's the case every time. That's something you should keep in mind as an engineer. Who invented the phone? Anyone know? Or at least, let's say, not the phone. Who invented mobile phones? Who or which company? What comes to mind when you think of modern day phones? iPhone, right? iPhone, smartphones, Android, whatever. But which company actually came up with the first mobile phone? Motorola. Motorola was the one that came up with the first mobile phone ever in New York City, 1980s, I want to say, or close to 1990s. They are the ones who held all those patents. There was a period of time a few years ago where Google actually purchased Motorola. They purchased Motorola for all their patents. There was more than 10,000 patents pertaining to communications and systems. So all other companies came later on. But the phone, the actual mobile phone system, the cell towers, everything that we're talking about, Motorola is attributed with that. But Motorola is not the only one that came up. They came up with the actual product that worked, right? So there's a lot of companies that came before it, a lot of companies that came after it. Motorola was the first company that actually is attributed with the invention of that phone. Smartphones, there was BlackBerry, there was Palm Pilot, there were a lot of other companies long before Apple came along. Okay. Anyway, that was a little segue. Let's come back to our point. So Ohm's law, named after George Ohm, came up with this law based on physics. One of the most important laws in physics and electrical engineering as pertains to a resistor, voltage is directly proportional to the current and vice versa. Constant of proportionality is the value of the resistor itself. So the equation is V equals IR. Voltage for a resistor is directly proportional to the product of the, is equal to the product of the current and the resistor itself. There are many other ways of stating this. If current passes through a resistor, it causes a voltage drop that is equal to the product of the current and the resistance. So V equals IR. Have you all taken the physics prereqs, I'm assuming, without which they would not allow you to register for the class? Right? So in physics, you learned about Ohm's law. Did you learn about KVL? KCL? Right? So Ohm's law, KVL, KCL, these three form the foundation of circuit analysis. You only need to know these three. If you're able to apply these quickly, efficiently, and correctly, you're good. Even as an electrical engineer, these are the only three things that you need to know. Everything else, all other analysis techniques are derived from these three. Node voltage analysis, mesh current analysis, current division, voltage division, superposition, resistive analysis, everything is everything is derived from these three. So these three are the most important: Ohm's law, KVL, KCL. Once you know these three, you're good. Okay, so as I was saying, voltage is directly proportional to current. V equals IR. That is the most important equation that we will use. Okay. I got time. Okay. All right. So constant function, right? We just talked about an example of a battery where the value of the battery doesn't change. It remains constant, right? So when you plot it as a function of time, the value does not change. Here we're talking about voltage and current. So we're going to talk about the sources and what different kinds of sources that we encounter, right? So here's a symbol for a voltage source. Here is a symbol for a current source. So if you see a circle and the circle has plus and minus signs in it, that refers to a voltage source. And if you have a circle with a arrow through it, it's referred to as a current source. So what do you notice here? We notice that voltage is always indicated with a plus and minus sign, and current is always indicated with an arrow. Okay, the arrow is not at an angle. Okay, it always points in line with the branch. If the arrow is at an angle, that indicates it's a meter. It's no longer used as widely as it once was, but if you have an arrow at an angle, it indicates the dial that's inside an analog meter. So if an arrow is at an angle, it indicates it's a meter, not a current source. For a current source, the arrow would be pointing in line with the branch. This is the branch. These two are the branches. So it will be pointing in line. Okay, so can we have voltage without current? Can we have current without voltage? What do you think? Yes and no, kind of. So here's the thing. I would say they always go hand in hand. You cannot have voltage without current. You cannot have current without voltage, at least as it pertains to a live circuit. Okay. But think about your power outlets. Your power outlets right now are live. There is voltage on those power outlets, but there is no current because we haven't plugged anything into that power outlet. So it's an open circuit. Yet voltage is present. If you measure the voltage, in there with the meter, it will tell us that there is voltage that is present. It's a live outlet. But there is no current flowing because there is no circuit. So the caveat is, if you plug something in there, it's a closed circuit. Now current has a pathway to flow, so current will start flowing. Okay. But in general terms, if you have a circuit and it's a live active circuit, that means you have voltage and you have current present together. You cannot have one without the other. So what makes it a voltage source and a current source? In real life, a current source is the same as a voltage source. It's the same box. There's no difference. If you look behind you on those lab benches, there are 8 lab benches. There's a function generator, a multimeter, an oscilloscope, source meter, and I believe right on the top next to the, let's say, which one? Can't state for certain which one from here, but one of them is a triple DC power supply. It's a DC power supply. Now the power supply is both a voltage source and is also a current source. The one on the bottom? Okay, great, thanks. So it should have 6 or 7 terminals in the bottom. Yeah, it does look like it has 7. I can't do, it's everything's a blur that far out for me. So yeah, that's a DC power supply. DC power supply can supply both voltage, it can supply both current, right? What makes it a voltage source or a current source is the mode of operation. If we run that box or that equipment, and I'll explain with an example in a minute. If we run it in constant voltage mode, CV mode, it is a voltage source. If we run it in constant current mode, it is a current source. That's the only difference. Okay. And I will explain with an example. Now a battery, typical battery, doesn't matter what kind of battery it is, it's always a DC voltage source. Because again, as I said, right, its voltage value, ignore its age, ignore the temperature, ignore pressure, ignore everything else. Hypothetically or theoretically speaking, a 1.5 volt battery is 1.5 volt at 8 o'clock in the morning today, and 10 years from now, it'll still be 1.5 volts, right? Ignoring everything. Constant voltage, but it cannot sustain constant current, right? So DC battery in that sense is a constant voltage source. Now, constant voltage or constant current refers to the fact that a source will supply its rated quantity irrespective of what is connected at its output terminals. Meaning, if you are running that power supply in constant voltage mode, let's say to supply 10 volts at its output terminals, it will keep those terminals at 10 volts no matter what you connect at those terminals. Same thing with constant current. constant current mode, let's say you set it to run at 1 amp. It will supply 1 amp at its output terminals, no matter what you connect at those terminals. And that's what makes it constant voltage. That's what makes it constant current. And that's what makes it a voltage source or a current source. In reality or in real life, they're one and the same thing. It's just the mode of operation that is different. So let's do an example. We just saw Ohm's law, V equals IR, right? This supply voltage is 10 volts. So V equals 10. If R equals 100 ohm, what is I? V equals I times R. V is 10, R is 100. What is I? Come on, even my elementary school son would be able to do this. Yeah, 0.1. So it's 0.1 amp. Now, let's say we remove that 100 ohm resistor from the terminals and we connect a 10 ohm resistor across those terminals. What is the voltage source supposed to do? It is supposed to keep the voltage constant at 10, but it will change the current to match the requirement of the load. And so now I is 1 amp. And that's what makes it a voltage source, because the voltage is kept constant irrespective of what is connected at its output terminals. Let's take a pause while that sinks in and let me know if you have any questions. Yes. So question being asked is about the omega sign. I should probably draw it a bit better. It's a good question. That omega represents ohms. And so omega represents ohms. That is the unit for resistance, which is something that we will learn again, I think, later on in this. Sometimes the units are weird, okay? If we, as per, just going on a little bit of a tangent, um, when you read the letter C in physics, what does it make you think of? The speed of light is 1. Yes, absolutely. What else? Coulombs. Yes, absolutely. Capacitance. Yes, that is correct. Anything else? Yeah, that's true. But that's, a little bit out there. But anyway, you get my point, right? The same letter is sometimes used for multiple different things. Right? Same letter sometimes used for multiple different things. It is up to us as engineers or as students or engineers to understand in context. Right? So I think ohms or omega, the Greek letter omega is the only one that I can think of that is used for units. Everything else is letters. Current is amperes, so we use A, amps. Voltage is named after volta, so volts, V, right? Power is named after Watt, James Watt, so W. Energy, joule, J. Everything's, yeah. So here's the question. What if R is equal to 0? What happens to I? Just mathematically speaking. Infinity. Infinity. So there are lots of important conclusions and points to note here. Okay. The first is R can never be zero. R equal to zero means it's a short circuit, meaning you're shorting out your terminals, you're shorting out any 2 points in your circuit. That's what it means when R is equal to zero, right? Second, if there's a short circuit and R is zero and there's voltage in there, doesn't matter how small the voltage is. If the voltage is 1 volt or the voltage is 0.1 volt, 0.00001 volt, technically your current is going to be infinite. So resistor, the humble resistor, is a very, very, very important component in an electrical system. We cannot build an electric circuit without a resistor. That's why we need resistors. We need them to oppose the flow of current. It seems counterintuitive, it seems counterproductive, but we cannot build a circuit without a resistor. Less than 4 minutes. Let's move on. All right, so I goes to infinity, right? And that's why we always want to avoid that. Now, in all these benchtop power supplies, these are known as benchtop power supplies, by the way. So in all these benchtop power supplies, there is a current limit function. We don't want a circuit to be blown out. Okay, if you have a resistor of just 1 ohm and you connect a 10-volt source to it, the resistor is only rated for like a quarter watt. Well, it's going to be 10 watts, 1 amp time 1 times 10. So 10 watts is going to blow out your resistor, a lot of thermal energy. So we put a current limit on there. So every single time you're using the lab, the first thing you should do when you turn on the power supply is check with the instructor on what current limit you should set. Otherwise, you're going to end up blowing out your circuit as well as the power supply, just in case you inadvertently short out your terminals, because the current will go to infinite. Let me give you a real life example. Few years ago, Samsung released a phone, just Samsung Galaxy Note 7. Anyone know what was so special about that phone? It blew up. It came to be known as the exploding phone. I wanted to get one, but I didn't. And I don't buy expensive phones anymore. So what happened there was, in the pursuit of making phones thinner and thinner and thinner, engineers in the battery department, they decided to make the walls between the battery. So the batteries are comprised of multiple cells and they're linked together. So they made the walls of these cells very thin, inadvertently shorting out the positive and negative terminals. When you short out the positive and negative terminals, what happens? Current goes to infinite. All of the energy that is stored in that battery is now released all at once. Now, if it's a limited capacity, it's going to release it and stop. But a cell phone battery is about 4,000 or 5,000 milliampere hours. So that's a huge capacity. Phones last at least a day, right? So that's a huge capacity. And so that is transferring current. Infinite current is flowing through and through and through. Think back to at the beginning of this lecture. What did we talk about? Energy is converted. Electrical energy is primarily converted into heat. So it's getting hotter and hotter and hotter and hotter, and then boom. And that's what happens. And so that's what happened to that phone. So it's a short circuit caused infinite amount of energy to be released. And there was no controlling that reaction. It was releasing a large amount of heat, which was unsustainable, and then it exploded. That's what happened. All right, and the final minute that I have, just talk about, this is an exercise for students to do on their own. What happens if you have a current source, let's say IS of 1 amp, and you're applying it to a resistor of, let's say 100 ohms, 10 ohms, and 1 ohm. These annotations are available to you, by the way, at your end in the class notebook, okay? So what is the voltage? That's an exercise you can do outside of class. And so also to make you understand how a current source will change the voltage at its terminals to supply its rated current. based on different resistors that are connected. Okay, and that's what makes it a constant current source. All right, we'll end class here today. We'll pick up here on Wednesday. We'll go at a slightly faster pace from Wednesday onwards.